Hi, my name is Kaajol. I've been at NVIDIA for about 3 years, and I also work on the product security tools team.
All right, we're going to talk about streamlining container security and how to get VEX in the right place so you don't have to redo it over and over and over again for all of the different products. Okay, so we actually talked last year about a really similar topic, VEX inheritance. And so since October of 23, NVIDIA has been publishing VEX for the NVIDIA AI Enterprise container images that are published on the NGC catalog. And so we created tooling back in 23 for syncing all of the OSS vulnerability reports and then having the ability then to put in the VEX status and justification and details, get that reviewed, and we have an approval process through that tooling. And then we actually have a publishing process as well. So when that container image gets published, then the publishing pipeline calls the VEX tooling and publishes the VEX in Cyclone DX format on the NGC catalog. So that was all back in 23. We had a very small subset that we started the VEX publishing process with, but we soon found that, hey, we were writing the same VEX over and over and over again. For one, the same actual release, right? Like let's say you do a build, you get a container image. We had no way to say that this container image is the same product as the next container image. But it's just like we're still working on the same release. So we had this idea of we'll tell the product teams to use a tagging schema that will allow us to inherit the VEX that's been approved between the releases from one build to the next. And then similarly, we had an idea to copy or clone the VEX from one release to the other with the similar tagging schema. We went back to the product teams and they were like, yeah, no, we don't ever actually use the same tag. We use like a commit SHA for our tag. And so we then determine which one is the release candidate. And you have no idea which one came first and which one came later based on the tag. So we've come up with some new ideas. So we will talk about VEX inheritance. We'll talk about another concept that we've coined global VEX. And then we will give you some proposed approach that we worked on design earlier in 2024, how we implemented some of that, and then some of the limitations and some of the lessons learned that we came across. Yeah, so the complexity here, right, is that it's really difficult to determine from one container image build to the next, that is the lineage from one to the next, right? That the vulnerability analysis should apply for all of those. And so we have these two terms here, VEX inheritance, which we are using to state that when we have a parent image, and parent image in this case is any image in the lineage of your final image, you should be able to determine what the vulnerability analysis is in many cases for that parent image and inherit that to the final image so that during the release of your final image, you have already done a lot of the analysis for the parent image for both the OSS licensing and also the vulnerability details. And you should be able to do a diff on if the parent image and the final image have the exact same SBOM or the same list of OSS packages and the same vulnerabilities, and then inherit, in most cases, those VEX. The other concept here is the global VEX. This is where we are using a policy to define in our scanning tooling, scan tooling, when we find the open source patched versions, so these custom versions, right? Like we took the open source, we forked it, we actually patched something. And so now we're naming the open source. Basically, it's the same version, but it's like we fixed this, right? And we can map the vulnerability details that we fixed in that patched version, add it to this policy, detect that whenever we're scanning the container image. And anywhere we see that custom OSS version, then we should be able to apply that patched VEX status. So that allows us to do this across the board wherever we're using those patched versions. That's the global VEX term here. For VEX inheritance, the key steps really are, we want to catalog the approved parent images. And the parent image in this case is really the largest subset of open source that is reusable or shareable among multiple applications. So that's kind of what we're trying to get to at the parent image. We add these to our catalog with a specific use case because those approved parent images, we want to make sure that we know which use cases that those are approved for and which application groups those are approved for. Then after they are added to the approved parent image registry, then we can look at the vulnerability details. We can associate any VEX. We can go through any license approval process we need to and associate those to the parent image. Once we have the final image built and we do the scan on that final image, we get an SBOM for the final image. We can also detect which parent image it was built upon, and then we can do a diff. So we can say, here's the SBOM of the parent image, here's the SBOM of the final image, and determine the difference of those open source packages and vulnerabilities. And you only have to then go through that analysis before you can release. So the goal is to cut down on how quickly or how much work you need to do for release for each of those final images. I talked about the approved parent image being anywhere in that lineage. So that's kind of what this image is trying to talk about. It does not have to be the initial base image of that final image, right? We know that we have a base image. You could build something on top of that. You could add in open source packages. You could take that next layer, that parent image number 1 there. We could add in some NVIDIA proprietary libraries there. Then a product team could say, oh, and I need some other libraries. So they'll create another layer, another parent image on top of that one. We really want to get to, like I said, the largest common set of open source so that we can set that as a use case, take that through any of the compliance tasks and the vulnerability analysis, and then we can share that across all of those applications that end up using that parent image. It's important to define ownership of those approved parent images because somebody needs to maintain these, right? When there are new vulnerabilities found, we need to be able to analyze that and add in more VEX, or we may need to say, hey, you can no longer use that approved parent image. It is now not valid for use. You have to use the upgraded approved parent image. And so we do have that tracking built into our catalog as well. We have like an expiration date. So you could set that whenever one approved parent image is no longer valid for use.
So Jessica mentioned this earlier, but we have coined a term called global VEX within our. We have coined a term called global VEX within our container scanning workflow. So global VEX is a way for us to globally generate and apply VEX documents for OSS patches, either from internal developments or from third-party partnerships that we have with other vendors. And so this allows us to manage the usage of these private OSS patches. So this includes automating the detection of the OSS patches, generating the VEX documents, and then applying the VEX to the reports so that whatever the patches that are used, we just filter those out from the vulnerability reports to reduce the noise. We also have a way to use the global VEX to provide upgrade guidance to teams. So whenever the patches do become available, we can enhance the visibility and streamline the adoption of the internally available patch software so that developers that could be like trying to mitigate a vulnerability, they would know that there is a patch version available either from a vendor or internally developed. So this really helps to reduce the noise and streamline how we can globally manage these patch versions.
Okay. Hopefully you can follow the picture. But I wanted to walk through kind of how our product catalog, our scanning infrastructure, and then our VEX tooling work together to allow us to register the parent images, and then where there are people here at play. So a user or API would register that parent image. We add it into the parent image registry using a ticketing workflow today. And then the image, as soon as it's registered, will go through scanning. So you see that number 2 down here to the container scanning infrastructure. The container scanning infrastructure updates reports in the product catalog. those reports will generate license reports and will generate vulnerability reports. And so the license reports can be used to create the OSS license ticketing process. So this is where our review board at NVIDIA will review all of the OSS licenses that are going into that product. Then you can also go into you can view the vulnerability reports in the product catalog, and then you can go into the VEX tooling to actually add in any analysis for the vulnerabilities and have that get submitted for a review approval process as well. So none of the VEX are ready to publish until they get approved by the product owner of the, right now, the AI enterprise catalog. So they go through the VEX tooling. They can then go back to the reports and they can see that the vulnerabilities that have approved VEX will fall off of the priority list and they now get added to a different report for the VEX list. The OSRB ticket, the open source review board ticket, is also tracked in the product catalog and it notes exactly the SBOM for that parent image. So we now have tracking on what was approved in terms of the SBOM, all of the OSS, and what vulnerabilities were approved for that parent image. Next, we register a final image. And in both cases, right, we have this like concept of a use case for the parent image, and the use case must match for the final image as well. So you register the final image, it gets scanned using that same container scanning infrastructure. This time, though, it will also look to see if it has a approved parent image in that list from that use case. So it will check to see if it has a compliant approved parent image. If it does, then it will show that in the reports. It's using this approved parent image, and it will also create a SBOM comparison between the parent image and the final image. So you can see any open source that was added on top of that parent image. You can then take that subset of open source packages and licenses to the review board so they can look at a much smaller list of licenses for compliance. Or if there is no extra open source added to the parent image, then it does not need to go through the review board. And so they'll get an automatic approval for the OSRB ticketing process. So that part of the release is checked and ready to go. For vulnerabilities, again, if there's no new open source, there's likely no new vulnerabilities, although there could be a new one published, and then you should actually go back to the parent image and add the VEX there. But if there's no new vulnerabilities, then they get a check for that part of the release process as well. If there is new OSS and there are vulnerabilities associated there, then they will just see the difference between the vulnerabilities that have already been vexed and the vulnerabilities that need their analysis. They can go to the VEX tooling and add in the analysis for that.
So once the approved parent images are registered in the product catalog, the next part of it is to actually shift compliance left and provide in-pipeline scanning and detection. So before build, developers are encouraged to use the product catalog to find approved parent images that match their use case. The in-pipeline jobs are enabled to detect the parent image by use case, determine if the parent image is approved for that use case, and then if it is approved, it can apply the parent image VEX on top of the container scan vulnerability reports. So the reports that are provided to the developer in pipeline tell the developer if it's using an approved parent image, and it provides only the vulnerabilities that need to be triaged that are not coming from the parent image. So these jobs can also be used to block pipelines, for example, if maybe they aren't using compliant parent images, and kind of just shift these features left and start in the pipeline. So throughout this process, we have found some limitations with the automated parent image detection. So the way that the automated parent image detection works is that it uses the image layers between the parent image and the final image, and it will try to match those layers. And so if all of the parent image layers are found in the final image, then that is how a parent image is determined. So while this process does work, sometimes we have seen that there are cases where we use tools like registry operation tools like Scopio or Crane. These are both open source tools. And these tools provide metadata on the image, like the image layer digest, the size, the architecture, all without requiring a Docker daemon to be present. And so these tools are very quick at doing this image metadata analysis. However, we have found that there are cases where the detection can be unreliable based on varying registry storage mechanisms, such as the compression algorithms used by the registry. So in order to address these issues, we also recommend integrating the build configuration explicitly to provide the apparent image details. So kind of going to back to our pipeline diagram. In cases where the detection fails, we also can ingest the parent image used in the image build configuration as part of the pipeline flow. So in these cases, we really want to ensure that the parent image configuration used is actually being used to build the final image. So this can be done either through Docker file scanning to find that last parent image or this lineage of parent images used, or it can be done through like a custom build configuration if there is like a custom build process that's used to do the build for the final image. And then we continue on to the same process of checking if the parent image is approved. If it is approved, applying the parent image VEX. And then we also will cache the parent images in the final image association in our product catalog. So when it does come time for release, we don't just have this information in our pipeline, but we also have it available in our product catalog, and we can enable the SBOM difference and the license approvals at that time as well.
So we have added in the ability to, when you're detecting the SBOM diff, know if an OSS package was added in the other layer, right? Like if that OSS package came from the final layer or from the parent image, and which one of those the vulnerability was associated to. So if the vulnerability was associated to the parent image, then we can inherit, in most cases, the VEX for that. We don't want to inherit the VEX details for a vulnerability that was also added in the final image, because we're not sure if that had the right analysis applied to it. But there are other cases as well that you want to kind of review before publishing these VEX status. Like a lot of these are the not affected mitigation ones. So if something requires configuration, you just want somebody to review that the configuration has not changed in that final image, that would now make that vulnerability exploitable. Similar with the dependency and with environment. So we're working on trying to add in more details that then we can detect as we are, rolling out or building that final image to make sure that we don't need to change these VEX status. So some of the lessons learned, we did actually pilot this in November of 2024. So this has been live for one of our first product since then. One of the big things we learned is that there was not really a great definition of who was going to maintain the parent images. So we were a part of the core product security team. And when we told the product team, hey, we're going to give you this great feature, they were like, great, that means you're going to manage all of our parent images. And we were like, no, actually, we're not. We're going to detect them. We still need you to maintain them and make sure that they work for your application. So there was a little bit of a hiccup there. So we're still kind of working with the product team to make sure that they have owners on their side for all of those parent images and that they are making sure to keep those up to date, test, and do any sort of release cadence that is necessary. Again, that parent image is the largest common set of open source that's shareable between multiple releases, multiple products. And so it really makes sense, right, that the product team owns that so they can make sure that they're testing it in the use case that they need it for. Let's see, I think I hit all of that. Next steps. Yeah, so we definitely want to do more automation. We have found that there are a big subset of the approved parent images are actually images that our company already releases as core AI enterprise images. And so those are used in some more of our products. Those get released and patched already on a monthly basis. And today there's this ticketing process that requires the team to go through to say, hey, I've got a new release of this parent image. Please add it and the digest of that parent image to the tool so that it can be used as a compliant parent image. And we need to figure out a way, can we automate adding in those new releases of these parent images? We have not found a great way to do that yet. The global VEX mappings. So today we get a list of VEX details from a vendor that says this open source package with this new version, this custom version, has this vulnerability patched. And we have to have somebody manually go and add this to one of our policies, the scan policy, that then we do post-processing on that will automate creating the VEX for that package version vulnerability combination. And so we'd love a way to ingest that and just automatically create the policy that we need to find all of these vulnerabilities wherever they are in any product. Similarly, when there is a NVIDIA generated patch for open source, so when we fork that open source and we create that patch, it'd be great if we could use AI to find that that patch was done and generate the VEX for that, and then find that vulnerability mapping to the custom version in the global VEX mappings. So we do have a tool at NVIDIA that is released, the vulnerability analysis for container scanner agent blueprint. It is quite a mouthful. The blueprint is open source. So you can find it on NVIDIA's website. I'm sorry to not link it here. But it does actually take a container image, the SBOM for that container image, and it will do analysis to determine what the suggested VEX details should be. So we're also integrating that into our workflow so that we can suggest any of the analysis also on these parent images, and then on the final image as well. So we really want to be able to do as much suggestion as possible and then have the analyst, yes, review all of that in the end and show which of these came from the parent image, which of these came from AI. Like we think this is, AI thinks that this is the analysis for this vulnerability, and which we can just not give with any great accuracy, any sort of suggestion. So that we're trying to kind of build that whole trifecta into our reporting tooling. I think that might be it. Did you have anything else you wanted to add? Okay. Any questions? Anything that wasn't clear? I know we.
There's a question on the Discord. Is the vulnerability analysis reused for the common software component so you don't have to redo it for each VEX statement?
I think so, unless that's a trick question. Yes.
Any questions in the room?
So just maybe I didn't understand this. So all of the VEXs that you issue are for the patched OSS components or for other vulnerabilities as well?
Other ones as well. So we have for patched, and that's mostly for using the global VEX. And then we have unaffected, false positive, and unaffected, false positive. I think so. Triage exploitable, but we don't really issue VEXs for those.
Okay.
They're just kind of like left out right now. And so there is a scanning tool on the NGC catalog. It will show all the vulnerabilities, and then it will show the VEX details for the ones that are not exploitable.
And when you issue VEXs for vulnerabilities on the non-patch OSS components, do you inherit those as well?
Yes, in most cases we do.
Okay.
There are some that, like if it requires configuration or, an environment or dependency, then we want the release, the product manager that's releasing to make sure that those have not, or like the security pick that's releasing to make sure that that has not changed.
Okay. Yeah. Thanks.
Yeah.
Oh.
Hello. Do you have any like enforcement steps in place in the build pipeline to like ensure people are using these maintained parent images, for example?
So today we're really kind of selling this as like an efficiency booster, right? So that you don't have to go, the product manager doesn't have to go through the open source review board and the vulnerability analysis for every final image that's going through. But we are working closely with the product teams to try to put a gate as well on the build pipeline. Mostly because we're finding that, unfortunately, some teams are still using versions old parent images, and so they really want to get away from that. So it's more to move everybody to the latest and greatest versions of those parent images. It is a little bit hard, right, to find the right net for how many parent images should be in that approved parent image registry for a use case. So that's kind of where we're having a hard time determining, can we really block the pipeline for that or not? That makes sense.
Thank you.